On this episode of MRI Physics Explained, the day has arrived. We're finally going to demystify one of the most confusing subjects in all of MRI physics, K-space. I know a lot of you have waited a very long time for a video on this subject, and I promise you all, by the end of it, you're never going to look at this misleading picture the same way again. So let's get to it and finally talk about K-space in this pivotal episode of MRI Physics Explained. Hello everyone, Dr. TE here. I know you're excited for this lecture, and I'm excited as well. Now, if you've seen the initial core lecture series which followed the traditional teachings of MRI physics, you'll notice K-space is not mentioned once. And that's why it's so perplexing when you're shown this picture, told it's frequency space, and it's somehow related to our final MRI image. So we had to completely change our understanding of MRI physics, beginning with a dedicated lecture on the Fourier transform and how it works. You can watch this lecture here, link above. That discussion led into the mathematics behind MRI imaging, which I apologize is a little math heavy, but essential to prove this relationship between the Fourier transform and our raw MRI signal. Now, for those of you that feel overwhelmed by the math, but still want to learn about K-space, then don't worry. You can still follow along the majority of this lecture and walk away with a good understanding of what's going on. But let me give you all a quick recap on how we came up with these variables, Kx and Ky. On the last lecture, we derived this complicated looking formula which shows that S of t, the signal measured over time, equals the sum of these two products, the proton density throughout the slice we wish to image times the amount of phase shift we induce within the slice using our x and y gradient fields, integrated at all points x and y within the slice. By performing some more math, we were able to put this equation into the form of a two-dimensional Fourier transform. Don't panic, I know it looks complicated, but it's not the emphasis of this lecture. Just notice that purely through math, we were able to show that this signal we capture over time equals frequencies coming from the slice. It's still our recorded signal, but we've done something to that signal. We've applied magnetic field gradients across the x and y axes for a certain period of time. So then how do we get our picture? We're trying to solve for this, the proton density within the slice, and to do that, we take an inverse Fourier transform of our raw recorded signal. We're going to illustrate this process throughout this lecture in a hopefully intuitive way. So that is where we left off, knowing that we need to record a raw signal on which we've applied these gradients, gx and gy, over time, which brings us to the topic of K-space. But first, if you enjoy these videos, consider liking and commenting, following us on social media, hit the join button to see ways you can support us further, and click that subscribe button below. So for those of you who've taken an MRI physics course for medical professionals, this is probably the image that comes to mind whenever you think about K-space. And to be honest, it sets all of us up for failure because if you tell anyone that this image leads to this, our brains will naturally try to connect the two. My brain is doing it right now, even though I know this relationship is 100% false. This picture has little, if any, usefulness when it comes to understanding how we build an MRI image, as we'll see shortly. So what is K-space then? K-space is simply our raw MRI data. We proved that with a little math, this signal recorded over time equals these variables Kx and Ky, and we need to store this digital signal somewhere, what we call the K-space matrix, denoted by these brackets. This is simply a table of numbers recorded over time. But where is time, you may ask? All I see are these variables Kx and Ky. Remember what these variables represent. Gradient magnetic fields applied over time. Time is actually in these variables. So when a course shows you this picture and says we go from real space to frequency space, and you naturally think, what do you mean? What happened to time? Your gut was onto something. We can never stop the flow of time, and time remains a major player in this thing called frequency space. Now you also might ask, why do we use the letter K? The K in K-space stands for frequency, which comes from old physics notation. Not intuitive, just the way the cards have fallen. These variables Kx and Ky also have units, and we can figure them out using unit analysis like we did in the previous lecture. If we look at the units of each of these components, gamma, which is in megahertz per Tesla, g of x, which is Tesla per centimeters, and time in seconds, then by adding this conversion factor of megahertz, which is 1,000,000 cycles per second, we can multiply these units out, many of which cancel, and which leaves us with cycles per centimeter, the units of K-space, meaning how many cycles of rotation the little magnets we've built up within our slice have accumulated depending on their location centimeters within the slice. Finally, it's critical to remember that each data point in K-space represents signal coming from the entire slice. This is why this relationship is wrong. 1 point here does not equal 1 point here. It equals data from the entire slice. Now I know you must be wondering, what does this data point visually look like with respect to our MRI picture? And that will be the subject of the next lecture on image building, where we tie this all together. But I can show you what K-space looks like, and here it is. Numbers. Digitized signal recorded over time for however many cycles we choose. Let's now visually demonstrate this by filling a line of K-space. We'll start with the basics. These animations should look pretty familiar by now. We have a slice of the body that we want to image, in this case the head. This slice is sitting in the XY plane, and we've placed this coil of wire which acts like an antenna along the Y-axis shown in blue. If we look at this from the side, our main magnetic field, B0, is running through the slice parallel to our Z-axis. This magnetic field B0 creates a magnet within our body, M-net, at rest aligned with our B0 field. This M-net can be arbitrarily divided into smaller components coming from however many voxels we break this slice into, and this allows us to better visualize what happens when we apply our gradients and other things, but summed together, these equal our total M-net from the entire slice, which is ultimately what our coil sees. Now we said K-space was simply our raw recorded signal, so let's record our signal, or in other words, make a measurement of the current we generate in our coil while this M-net rotates after our RF pulse. Let's say when we record the signal at this point, we measure 0.7 amps within the coil. Our next measurement is when M-net is perpendicular to the coil, which happens to be the maximum value we'll generate, 1 amp in this case. Next, again we measure 0.7 amps. Now our M-net is parallel to the coil, where through Faraday's law, we'll record no signal, 0 amps. Let's follow this a little longer. Now M-net is rotating away from the coil, so we'll measure negative 0.7 amps, followed by negative 1 amp. So if we put this into a table, it might look something like this. We've recorded 6 measurements of our M-net generating current over time. But does this look like the K-space I showed you? Looking back at this real picture of K-space, notice that there are 2 numbers, one real and one imaginary. It turns out the frequency data in a 2-dimensional Fourier transform is always represented by one real and one imaginary number, designated by the I symbol next to the second number in each pair. Now, not to get too into the math, you can still build an image with just one number like we showed in the example. But it's actually pretty easy to get our data into this exact form, and it has some benefits. Notice if you just use one coil, we run into this situation where M-net will produce the same value from 2 completely different positions. Is there a simple way we can determine the direction of rotation of our M-net? How about this? What if we just add a second coil, this time along the x-axis? We'll call our original coil along the y-axis our real channel, and this new coil along our x-axis our I channel. Now with two coils, notice that when MNet rotates, we're getting two different looks at it. Say we start recording now at this time point, 1 millisecond. Our real coil is measuring 0.7 amps, and our I coil is also measuring 0.7 amps. We can write this in a more mathematical form like this. Let's measure again at 2 milliseconds when MNet has rotated further. Our real coil measures 0 amps as before, but now we have this second coil that can detect MNet because of its different orientation, measuring 1 amp, put into our data matrix form here. Finally, we measure at 3 milliseconds, with our real coil measuring negative 0.7 amps and our I channel measuring positive 0.7 amps. Recorded here. Looking once again at the series of measurements we've recorded over time and comparing them to this actual picture of K-space data, what do you think? We've now recorded our raw signal in the format of the frequency data in a two-dimensional Fourier transform. And as a bonus, we can figure out the direction of rotation of our MNet with this two-coil setup. So now all we have to do is perform an inverse Fourier transform on this data, and we get a picture, right? Wrong, because in this example, we forgot to do something that's essential to this whole process. We didn't apply any of our gradient fields, gx or gy, across the slice to induce the frequencies in our signal necessary to build our picture. Let's take a look back on our pulse diagrams, this one of the standard spin echo sequence. Remember that we need to apply these two gradient fields as part of the sequence, traditionally labeled our frequency encoding gradient and our phase encoding gradient. These are really oversimplified terms representing the k values we are generating at these time points within the pulse sequence. Note that it doesn't matter which one we pick to apply where. Kx, which contains the gradient field across the x-axis, can be applied here, and vice versa with ky. What's more important is when we apply these gradients. One is applied during what we call signal readout, when the echo develops and we tell the computer to start recording the current generated within our receiver coils. And if you look at the math, then this gets really interesting. Take a look at this variable t here. This t corresponds with our main timeline. So mathematically speaking, as soon as we turn on this gx gradient and start recording our signal, this value kx is going to grow larger and larger as time goes on, meaning we can record a whole range of frequencies in just a single cycle. So why do we even have to do more than one cycle of this pulse sequence to build an image? Well, remember, we also need to collect frequencies in the y direction. We're trying to generate a two-dimensional picture with information needed in both the x and y dimensions. So we need to do the exact same thing with ky as we did with kx, but we have a problem. For various reasons, we cannot apply these at the same time. We only get one of these freebies, and so in order to generate different ky values, we're going to blip this other gradient on and off early in the cycle. This will embed one ky value into our signal per cycle, and so to get different ky values, each cycle we're going to either choose a different gradient strength, gy, and or a different length of time this gradient is applied, represented by the symbol tau. And it's important to note that tau, while occurring on the main timeline t, is its own unique fixed value for each cycle and is not changing when we record our data. Now that we've covered how we record data and this interplay between the gradients, signal, and pulse sequences, let's run through this process while visualizing how all these components work together. On the left, we have our slice of interest containing the magnets we've built up within each voxel of the slice, flanked by our real and I channel receiver coils positioned along the x and y axes. To the right, we have our data matrix, which is where we'll record our signal over time. To begin the process, we apply our initial RF pulse as usual, producing a free induction decay as described in the previous lectures. Then we'll generate an echo with another RF pulse or gradient field, not shown here. In reality, all of these magnets will be rotating in and out of phase with each other, getting more in phase as the echo starts to emerge, but visually let's pretend they're fairly well aligned going into the echo. When we're ready to start recording data, we'll turn on our gradient field and start recording the current being induced into our reel and eye receiver coils as the echo develops. Notice that this gradient field will cause more and more dephasing the longer it's applied. Now, if we look at this echo we recorded while applying our GX gradient, notice it's nice and strong. Let's place it here in the center of this table. This will make more sense as we go along. Now let's see what kind of an echo we develop if we run this sequence again, except this time also applying a very strong phase encoding gradient. We start with our RF pulse as usual, but now we'll apply our other gradient, GY, using a strong magnetic field across the y-axis for a chosen duration of time. This will cause dephasing along the y-axis as shown, until we turn the gradient off. We then do our usual tricks to generate an echo, and then once again turn on our GX gradient and begin recording the signal. You can see visually this gets pretty hard to follow as we now dephase across the x-axis, ultimately generating the following, placed here at the bottom of this picture. Notice how much weaker this echo is than before, because not only did we cause more dephasing with this GY gradient, we chose a very strong and/or lengthy gradient, causing the maximum amount of dephasing we want to achieve. Let's keep repeating this process, this time using a slightly weaker GY gradient, producing a slightly stronger echo. And again, and again, with a progressively weaker GY gradient. Where do we go from here? Why don't we now reverse the direction of the GY gradient and keep the process going, noticing that as our GY gradient is now getting stronger and stronger, our echo gets weaker and weaker due to the dephasing it causes. Now, first I want you to notice a sort of symmetry here between the top half and the bottom half of this picture, where we applied the same GY gradients just in reverse, so we would expect to get similar K-space values between the two, right? This is the fabled K-space symmetry that is always mentioned in courses, but be warned, this will only be present if we choose to fill K-space using these symmetric GY gradients. The second, and perhaps more important point, is remember what this matrix really is. Digitized signal recorded over time using two coils. Never forget that this is what K-space looks like. Numbers representing this physical process we're capturing, and these numbers can be used to calculate things such as images or relationships. For instance, we can calculate a magnitude between these two values. We can also determine what the phase angle is between them. It may also be of interest to us to take a look at either the real or imaginary component alone. For instance, let's take a look at the real component and assign a simple black and white color scheme to the numbers. The larger the value, the closer to white. The lower the value, the closer to black. What type of image would this produce? Dun dun dun! The infamous K-space image. Notice the obvious. This is not our MRI image. We have not performed the inverse Fourier transform on this data to create an image. It's simply showing a correlation between the gradient fields we applied and the strength of our recorded signal, the echo. Noting that when we apply the minimal amount of gradients, such as here where no GY gradient was applied, we'll get the strongest echo, highest recorded signal, and therefore the brightest area in this image. Alternatively, when we apply the maximum combination of gradients, we'll get the weakest echo due to dephasing, record the lowest signal, and therefore generate the darkest areas of this image, along with everything in between. So this is how we get the infamous picture of K-space, or frequency space as they call it, a visual tool that makes it easier for us humans to visualize our recorded signal strength, which will be determined by our pulse sequence technique and the gradients and amount of dephasing they cause. But notice that knowledge is somewhat lost in this picture. Think of it like baking a cookie, a delicious looking oatmeal raisin cookie. Yes, I know that oatmeal raisin is like the Canadian bacon and pineapple pizza of the cookie world, so if you prefer something else, then pretend it's that. But this cookie is the end result of several steps and ingredients that came before it. We can make very general assumptions from this picture, like they used raisins and oatmeal, but the most important information we really want to know, such as how they created this cookie, all the individual ingredients, how they mixed them, how long it was put in the oven, and at what temperature, this information cannot be deciphered from this picture. It's known only to the baker. Same thing with this picture of K-space, except even worse, at least the cookie was in the final form. This isn't even our MRI picture, nor is any human seeing this picture at any point in the process. If you go to the person running the MRI machine and ask to see K-space, they'll probably look at you like you're crazy. At least they did to me. So then what's the use of this picture? It embodies some of the principles we're trying to teach, but I think overall it does more harm than good and creates a lot of confusion. Even if there was something you could visually see from this picture that might improve image quality, at the end of the day, this is the only thing our machine sees, recorded numbers, and any operation to improve picture quality will be made by combing through these numbers, not by a technician looking at this image and making adjustments. Does that make sense to you all? Now, before we move on, there's one last issue we need to address: the order in which we recorded this data. Recall that initially, we started by recording the echo with only this gradient across the x-axis, giving us the center of this picture with the strongest echo. Then we applied the strongest GY gradient, giving us the weakest echo at the bottom, followed by slowly decreasing the GY value before reversing and increasing it to fill out the rest of the picture. So this was the order of cycles we filled in this data matrix, and when you really think about it, it doesn't make sense. I misled you, but it was for a good reason. I wanted you to first understand what these gradients do to the rotating magnets in our slice, and how they affect the echo as we record it, starting with the simplest situation when we have no phase encoding gradient, which unfortunately occurs at the center of our data collection on this image. But in doing so, this suggests that there is some important spatial arrangement of numbers we need to achieve when filling in this matrix, which is false. Remember that this is just an empty placeholder we record our data into line by line, starting from the top and continuing downward, so from a picture building standpoint, we can apply whatever gradients we want in whatever order we want. Our goal is not to make the picture on the right appear in a certain orientation. It's only to capture enough frequencies through our Kx and Ky variables to generate an understandable MRI image. That being said, there is a somewhat standardized way to go about applying these gradients in a traditional spin echo sequence, starting from the top with the maximum GY gradient and proceeding as shown. This is a very selective example that leads us into the next topic, which is another source of confusion: the order in which we fill K-space. We will always fill in this data matrix from top to bottom, starting with the first cycle, followed by the second, and so forth for however many cycles we want, with the time of each cycle of data collection moving from left to right. Remember, the order of the cycles has no bearing on our image formation. But in the example we've seen so far, we've applied our gradients in a unique fashion. Specifically, we used a constant Ky value for each cycle. We applied a constant strength of GY for a set amount of time, so the Ky value does not change along rows in our dataset. When we assign a color scheme to these data points to create the picture we're all familiar with, It's important to understand that this reflects the same process acquired cycle by cycle over time, using a constant ky value for each cycle. Also notice that we used the same gx gradient for every cycle. We didn't have to change gx because time was evolving as we recorded the signal. This is where it gets messy because we don't have to keep this gy gradient field constant with each cycle, nor do we have to keep the gx gradient field constant. We can actually change the gy and gx gradients within each cycle, illustrated by the following example. Notice now we are jumping across different k values within each cycle by changing the gradient strength or even reversing it during the cycle, and the direction of time no longer simply flows from left to right within the picture. The pathways of data collection and how we apply these gradients are limitless. We can even take more crazy-looking pathways such as this. However, while using these illustrations can be helpful in showing you the different ways we can collect data, it falls apart when really trying to understand this process of filling k-space, because we are trying to use this picture, which was created using a different combination of gradients and k-values, to reflect a new dataset. Remember, this picture is simply a color scheme reflecting the values recorded in our data matrix. It will always reflect the same cycles recorded over time. What actually happens is if we change the kx and ky values in weird ways by playing with the gradients during the cycle, our picture from this data will change to reflect those, such as this visual of k-space data from a haste sequence. Notice how much more radical the picture looks because we did crazy things with the gradients during the pulse sequence, and our echo reflects that. So this is why I really encourage you to look at this for what it really is. Data captured over time by our receiver coils with each point representing some value kx and ky which we control. Looking at it this way, we can perform as many cycles as we want, collecting more and more data for our image. We can also record each cycle for a longer period of time, or begin the recording earlier, collecting more frequencies, which will have very significant implications as far as imaging time and imaging quality, as we'll dive into on the next lecture. So now that we've hopefully flushed out these concepts, let's wrap this lecture up going through a few cycles and collecting data. We start the cycle as always with our RF pulse. And now that the system has been energized, we blip on and off our gy gradient for a set amount of time to get our first ky value. We do additional pulses or gradients to make an echo emerge, at which point we turn on our gx gradient while recording the current our echo generates in our coils. We then repeat the process, starting a new cycle with another RF pulse, again applying our gy gradient, but this time using a different field strength, followed by more RF pulses or gradients to make the echo emerge, and once again, turn on our gx gradient and record the signal as the echo develops. We're going to repeat this process over and over, each time selecting a different gradient field strength for gy until we've recorded a nice mix of values as our data set. Notice that each of these ky values is unique. We've applied a different field strength each cycle, and so the ky value will vary along columns of this table. In this example, ky is constant along each row, but again, it doesn't have to be this way. We're just following a standard spin echo sequence. Additionally, while we kept this gx gradient the same for each cycle, time was changing as we were applying this gradient while recording our signal, so our kx values will be changing along the rows of this table. Together, you can see that each recorded data point is going to consist of a unique combination of kx and ky values. kx1, ky1, kx2, ky2, kx3, ky5, kx7, ky6, and so forth. So at this point, there's only one thing left to do. If we designed our pulse sequence to generate enough unique combinations of these kx and ky values, then if we perform an inverse Fourier transform on this data matrix, we should, in theory, produce our MRI image. And that, my friends, is this entity we call K-space. Our raw data upon which we've encoded different frequencies in both the x and y directions by applying these gradient magnetic fields, Gx and Gy, at selected times in the pulse sequence. I hope this physical and mathematical perspective can finally demystify what this entity called K-space is. And while I think we've built a solid foundation to explain this whole process, there's one big question we've yet to explain. What's visually going on here? We know the math is sound, but how do these data points go from numbers into the images we've all come to know and love? On the next episode of MRI Physics Explained, we put the final piece of the puzzle into place on this series on how MRI physics really works by showing you in real time how we build a picture from our raw dataset, and in the process, unlock the full potential of MRI imaging. Thanks for your support, everyone. I know a lot of you have been waiting a long time for this lecture, and I hope it didn't disappoint. We'll see you next time for the epic conclusion. This is Dr. T.E. signing off.